Welcome back. In this video, we will learn how to write electron configurations for the main group elements. We'll do this using the extended and the noble gas electron configuration. We'll also determine the number of valence electrons for the S and P block elements based on their location on the periodic table. We've already seen that the periodic table can be divided into the 4 different blocks, and that these blocks represent the different subshells of the shells. The electron configuration of an atom describes the subshells where the electrons are located. And when electrons get filled into the subshells, they will fill the lowest energy subshells first. That's in order to maintain the lowest energy state possible. So this is showing you the first 8 energy levels from the periodic table. What's important to recognize here is that they follow the ordering of the subshells if you were to read them like a book page in English, where you read left to right, top to bottom. So we have the 1s, then the 2s, then the 2p, the 3s, the 3p, the 4s, the 3d, and the 4p. That's the ordering of the lowest energy subshells. And that's the ordering you would get if you read from left to right and top to bottom, reading it across the blocks of the periodic table. And so the higher energy subshells, the ones that are farther down, only become filled after we have filled all of the lowest energy subshells first. Let's take a look at some examples. For hydrogen, it's the first element of the periodic table. It has 1 proton and 1 electron. And so that electron goes into the 1s subshell. So we would designate that as being a 1s1. The 1s indicates the subshell where the electron is located, and the 1 as the superscript indicates the number of electrons in that subshell. Helium is element number 2. So it has 2 protons and 2 electrons. That second electron must go into the 1s subshell before we can start to fill up the 2s or the 2p. And that's because it wants to have the lowest energy state possible. So its configuration would be written as 1s2. There are 2 electrons in the 1s subshell. Lithium is element number 3. It has 3 electrons. And so we need to now put that 3rd electron into a new subshell. The next highest energy is the 2s. And so we have 2 electrons in the 1s and 1 in the 2s. And we can continue. Beryllium adds that 4th electron into the other 2s subshell spot. And boron, element number 5, adds the 5th electron into yet another subshell, into the 2p subshell. Now you can see that as we go farther across the periodic table, that these configurations could get very cumbersome. So we're going to use the core electron configurations to abbreviate. Helium, for example, as we saw, is written as 1s2. We could, however, just write this as helium in square brackets. And so elements that come in the next row after helium can use helium in square brackets as their core instead of having to write out 1s2. Lithium, for example, could be written as 1s2, 2s1, or it could be written as helium 2s1. And so we see using this notation that there are core electrons and valence electrons. Valence electrons are the electrons in the outermost shell. And those are the electrons that are going to react with other elements and molecules to perform chemical reactions. The core electrons are the electrons in the inner shells. And these are what are being abbreviated by the core electron, the notation, that noble gas symbol. Now, it doesn't seem like it's saving us much effort for the case of lithium or beryllium or boron, to write helium as a core. However, you can imagine that for larger elements, it gets more important. Argon, for example, it is element number 18. So it has 18 protons, 18 electrons. And so we fill out those electrons into the lowest energy subshells. So its configuration is 1s2, 2s2, 2p6, 3s2, 3p6. The next, and that ends that particular row. This could be written as neon 3s2, 3p6. And that's the same thing as argon. We could then use argon as a core for potassium. Instead of writing out 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, we just write argon in brackets, 4s1. And so you can see that it really does begin to simplify, and it helps us to be able to tell how many valence electrons there are. So to summarize, the elements within the same group, in the same column, they're going to have the same valence shell electron configuration. Their core will be different, and the subshell of their valence electrons is going to be different as we go down a group. However, they're going to have the same number of electrons within that subshell. And so that we'll see that they have the same number of valence electrons. So here's a problem similar to one that you might see on a celebration of knowledge. How many valence electrons are in a sulfur atom? Why don't you pause the video and see if you can figure this out? Welcome back. So in order to determine this, we need to locate sulfur on the periodic table. Elemental symbol S is number 16. And so it has 16 electrons total. Now that's the number of total electrons, not the number of valence electrons. By determining its group number, by determining its electron configuration, we can determine how many valence electrons there are. So sulfur is right here. If we were to determine its electron configuration, we'd put 2 electrons in the 1s, 2 in the 2s, 6 in the 2p, 2 in the 3s, and then 4 in the 3p. Now remember, we could write this with an abbreviated electron notation, and that would have neon as its core. Neon was this element right here. And then 3s2, 3p4. Those correspond to 6 electrons, and those 6 electrons are our valence electrons. And the shortcut is essentially, if you look at the group number for the main group elements, that will tell you the number of valence electrons. And so there are 2 types of group numbers when you look at the periodic table. There's the group numbers that have A and the group number that has B. The A labeling system tells you the labels for the main groups. So you'll have 1A here, 2A here, and then this is 3A, 4A, 5A, 6A, 7A, and 8A. And those numbers indicate for you the number of valence electrons within that group. All right, that's it for this video. Thanks very much for watching. Have a great day.